Continuing our discussion of different types of reactions, we're now going to focus on reduction and oxidation reactions. Another one that we'll talk about a lot more when we talk about electrochemistry this time. Now, oxidation reduction reactions or reduction oxidation reactions, it's kind of a mouthful. It's a reaction where electrons are actually transferred from one reactant to another. And kind of our abbreviated term for it is redox reactions, to kind of take the abbreviation of reduction and oxidation and combine it into one word. Now, this explains why I was so on my soapbox about the definition of an ionic bond, that there's no way it could be the transfer of an electron to another element, because that act of the transfer of the electron is a redox reaction. So it's a chemical reaction. Now, the bond that forms between two electrostatically charged particles, that's the ionic bond. And the reason I'm so picky about this is that redox chemistry is like so cool and does amazing things in biology. So there's lots of redox reactions out there. A lot of the transformations that your body catalyzes to undergo metabolism are redox reactions, and it's all about shuttling electrons around in your body. But some of them we see all the time, like the rusting of a nail is a redox reaction. We have electrons transfer from solid iron in its elemental state to oxygen, and we get this iron cation and these anion oxygen atoms that form iron oxide, which is rust. And that happens spontaneously. So we'll talk about that again some more when we talk about free energy. And then we have combustion, which is a category we're about to talk about in this lecture series, but it's actually just a combustion reaction, or sorry, just a redox reaction in its most fundamental state. And what's really happening is we're seeing oxygen take on electrons from the other material that it's reacting with, and forming these negatively charged oxygen atoms. And so we're having those be reduced. So let's talk some more about the language and how to recognize these. Now that I've convinced you they're the coolest reactions we have. So first, to identify that a redox reaction is taking place, that something is losing electrons and another reactant is gaining electrons, and that's that electron transfer. Something's losing it, something's gaining it, or snatching it from it, or giving it to, kind of half glass full, half empty with water. So to track that, we need to understand what we call oxidation states. And this sometimes is the same thing as the charge of something if it's an ion, but it also allows us to estimate something that's similar to a charge and something that's not charged. And so, especially for reactions that are not metal to metal reactions, where we see the charge of something obviously change, or reactions that don't involve oxygen, we need to see where the electrons are being transferred. And so it's been created this kind of bookkeeping method for electrons. And we have lots of bookkeeping methods in chemistry. We'll talk about them when we do bonding with Lewis dot structures. We'll have an electron bookkeeping method there. Here we're developing a bookkeeping method for tracking where electrons transfer to. And that's by tracking the oxidation states between the reactants and the products for each of the elements. And so I'm going to walk through how to assign an oxidation state, and then how to compare them to determine what's being oxidized and what's being reduced. Now remember, these are imaginary charges that we're going to use based on an algorithm, a set of rules that you're going to apply exactly as the rules state. They're not real, they're not measurable charges, but they will bring us to the right answer each time. So here are the rules, and this looks like a lot, but a lot of these are really intuitive already. So first of all, if an oxidation state for any sort of just element in its elemental state will be 0, kind of like just sodium metal has a charge of 0, it now also has an oxidation state of 0. Chlorine gas, well, that's just the elemental state of chlorine. So it'll have an oxidation state for those chlorine atoms of 0. So that one's pretty straightforward. Then anything that's an ion, like a monoatomic ion, so typically a metal or maybe a monoatomic nonmetal anion, will have an oxidation state equal to their charge. So oxidation state equals charge if it's just an atom with a charge, just an ion. And then we also know that the sum of the oxidation states for all atoms in a compound will be 0, just like when we did ionic bonding. So nothing really new yet, just this new word. We also know that the sum of oxidation states for all atoms in a polyatomic ion will then equal the charge of that polyatomic ion. And then that will get a little bit more complicated, but we'll address it in Rule 5. So basically, if you have a molecule with a charge, all your oxidation states need to equal that overall charge of the molecule. All right, now looking at Rule 4, Group 1 metals are going to have an oxidation state of +1. That's the charge they would have anyway. And any Group 2 metals will have an oxidation state of +2 in their compounds, also the charge they would have anyway in an ionic compound. And then in compounds with nonmetals, the oxidation states are going to be assigned by an order of priority that's ranked. So what needs to happen is that these rules need to be applied in assessing oxidation states in this order. So you start with rule 1, 2, 3. And a lot of these you'll skip because they won't apply to the molecule you're looking at. And the one where I feel like the most nuance comes in, like 1 through 4 usually take care of themselves pretty quickly. But number 5 is where you need to focus. And so I'm going to actually blow up this in the next slide so we can take a closer look at it. So these are also a priority order as well. So when you have nonmetals, you're going to assign oxidation states in this order. If fluorine is present, it gets to be -1 right away. Then if hydrogen is present, it gets to be +1. Oxygen, -2. Anything in group 7A gets to be -1. Those are our halogens. Then in 6A, it gets to be -2, and 5A, -3. And so you will put these in order, and you'll hit a point possibly where maybe you are down and you're trying to assign a group 5A metal, or non-metal, but everything else already has a oxidation state assigned to it. And if you assign the -3, you won't have the oxidation states equal the charge of the molecule, be that 0 or -1 or +1. And so you'll hit a point where sometimes you have to assign an oxidation state that isn't part of the rule set, just because the priority rule is that everything equals 0 if it's a neutral molecule. So let's do an example of that right here. Let's do 2 examples. Let's start with HNO2 first. So I don't have to apply my first 4 rules here because I have to have everything equal 0 because this is a neutral molecule. So my goal is to have all my oxidation states equal 0. But I don't have any metals here. And I don't have any ions. So I'm just going to apply these rules as they're listed here for nonmetals. So I'm going to start at the top. There's no fluorine. Okay, next it's hydrogen. So that means I assign the hydrogen's oxidation state first in this molecule. So it's going to be +1. Next is oxygen on my list. So I won't worry about nitrogen yet because nitrogen doesn't come until the very end of this. But hydrogen is first and oxygen will be second. So that means my oxygens are going to be -2 each. So what does that leave the nitrogen? I'm not going to come down and apply the rule that it's -3. Instead, since it's the last element in my priority list, I'm going to determine whatever number it needs to be for an oxidation state to equal 0. And so right now I have 1 hydrogen and it has a +1 oxidation state. And I have 2 oxygens with a -2 oxidation state. So I'm going to take that subscript and apply it to the oxidation state of that oxygen. I add these up and I am going to get, let's see, 1 plus -4. I'll have a -3. So for this to equal 0, this X is going to be the oxidation state of my nitrogen. And so the only thing it can be is +3. So that makes the oxidation state of the nitrogen +3. Now this is definitely not the rule, right? But it's the priority rule of making sure that this equals 0. So the oxidation state of my nitrogen equals 0. All right, now let's try another one. This one involves a metal. So we have sodium hydrogen phosphate, and we have a sodium and then this H2PO4. So right off the bat, I'm looking at this. I'm like, this is an ionic compound because I have a metal and then a pile of nonmetals, and I have a polyatomic ion. So this sodium will be a +1 charge because it's a group 1 metal. Or sorry, And so it also means that it'll be a +1 oxidation state. So I can assign that as +1. Now I know this H2PO4 has to add up to -1 because that's the charge of that polyatomic ion. So thinking about that, I'm going to focus on this piece here. So it has an overall -1 charge. I write that in the upper right-hand corner. So I'm going to go through my list of nonmetals again. No fluorine, but there's hydrogen. That's the first priority for this one. So these are all +1. Then I have my oxygen next before phosphate shows up. So these are all -2. So I'm not going to use the rule for phosphorus. Instead, I'm going to figure out what is left over and what do I need it to be to have an overall charge of -1 or overall oxidation state for that molecule. So I have 2 hydrogens and they're both +1. And I have 4 oxygens and they're all -2. So that gives me a total of -8 plus 2. It's -6. So that means to get to an overall -1 charge for this, my phosphorus oxidation state is going to need to be +5. So then that's going to be +5. So the oxidation state of my sodium is +1, my hydrogens are +1, my phosphorus is +5, and my oxygens are -2. So now that I have a way to talk about oxidation states and evaluate them, we can actually get back to what is reduction and what is oxidation. All right, so oxidation is the loss of an electron from an atom, and reduction is the gain of electrons from an atom by an atom. Now, if you're someone who easily flips things that are dichotomies in their head, or if you have mild dyslexia, then this is something that's really easy to get flipped up. So it takes a little practice and probably a weird acronym. There's a couple. Leo the lion says GER, so that's actually not what I know very well. So Leo the lion is loss of an electron, gain is reduction. The one I also know is oil rig, which is oxidation is loss of an electron, and reduction is the gain of an electron. That's one I remember best. You can look up Leo the lion says GER. And so this means that if we're oxidizing is losing electrons, then we have another phrase for it. Something that is oxidized is acting as a reducing agent. So it's going to make something else be reduced. And something that's reduced is going to be acting as oxidizing agent. It's going to force something else to be oxidized. My preferred terminology is oxidation and reduction. You will see in probably the sapling homework and in your textbook the phrases reducing agent and oxidizing agent. So just be aware that they're not interchangeable at all. In fact, they're opposites. And so let's look at a simple example looking at 2 metals. So we have zinc, an elemental zinc, combined with copper ions as our reactants. And they react to form zinc ions and copper as an element. And so what's happening here is we're going from an oxidation state on our zinc of 0 to an oxidation state of +2. So we're going from 0 to +2. That corresponds to a loss of electrons because we're gaining more positive charge. It means that there's an imbalance there. There's more protons and electrons. We've lost electrons to create that cation. And so that zinc is losing 2 electrons, and that means that our zinc is oxidized. Now our copper has a +2 oxidation state to begin with because it has a charge of +2. And when it goes to elemental state, it goes to an oxidation state of 0. And so we're going from a +2 to a 0. So to lose positive charge means you're really gaining negative charge. And so we're gaining 2 electrons in this process. And that's going to correspond to gaining electrons is reduction. So when we talk about reduction and oxidation, after we recognize which one is being oxidized and which one is being reduced, a helpful way of talking about this sometimes is to separate the reduction and the oxidation to look at them separately. And we call these half reactions because you can't have a reduction without an oxidation. They go together, they can't actually be separated in nature. But it's sometimes helpful to look at what is the oxidation process that's occurring and what is the reduction process that's occurring. And so here's how we write half reactions. So a half reaction is going to take the reactant and the product that's undergoing oxidation and have just them on either side of the arrow. So in this case, we identified zinc was losing electrons. It was being oxidized. So we have zinc and zinc plus 2. Now, when zinc transforms into zinc plus 2, it's losing 2 electrons. And so we write those 2 electrons on the product side. And so whatever we have for our charge on one side of an equation has to equal the charge on the other for these half reactions. And so for us to be able to have a 0 total charge on our reactant side and then a plus 2 charge on our product, we have to have a negative 2 charge as well. And that negative 2 charge is the 2 electrons that are released. Now we can write the reduction half reaction. And we already identified that copper is undergoing reduction as it gains electrons. So we start with a copper plus 2 in our reactant side, and it becomes copper, the element, in our product side. To do that, to gain those 2 electrons, we need to add 2 electrons to that copper 2 plus. And so we write the 2 electrons on the reactant side. And again, we can see that plus 2 and that minus 2 charge would cancel each other out and equal 0, which is the overall charge on our product side of the reaction. So again, these aren't full chemical equations. These are half reactions. One is describing the process of oxidation and one is describing the process of reduction. To make sure you've done this correctly, when you're looking at your half reactions, you should have the same number of electrons in the product side on your oxidation reaction that you have in the reactant side of your reduction equation. A few more notes about this before attempting a practice problem that I'll show a solution for. Um, and this is kind of highlighting some things I've already talked about, but I want to make sure crystal clear that oxidation and reduction have to occur simultaneously. It's not one and then it's not that the atom loses an electron, it hangs out, and then another atom takes it. It's that it happens at the same moment. And so this transfer of the electron happens right away. Then we also can look at the reactant that's reducing an element is going to be called the reducing agent. So anything that is the reducing agent is itself being oxidized. And this is kind of like a matter of perspective. It's oxidized when you consider what's happening to that chemical, but when you look at what it's doing to another chemical, it's reducing it. And I know that's anthropomorphizing molecules, and but it's a helpful way of remembering it. So then looking at it, we can say that any reactants that's oxidized an element in another reactant, that's going to be our oxidizing agent. So the oxidizing agent is going to contain the element that is reduced. So hopefully this helps as you navigate the language of oxidizing agent versus oxidized. Again, my preference is for reduced and oxidized, and just stick with those because it's simple. But you will see both versions of this out in the world as you study and learn this. So in our example down here of sodium and chlorine coming together to form sodium chloride, which is the typical example that people give for forming an ionic bond, it's really a redox reaction, we would say that sodium is oxidized while chlorine is reduced, or we could say that sodium is the reducing agent and chlorine is the oxidizing agent.